Great, so I can basically say whatever I want and it's going to be fine. Yeah, so vectors are a mathematical construct. And in math, basically, they're a construct that are, they're very good in encoding a direction and a length. And that's mostly what they're used for. So I don't know if anybody toyed with making games before or something like that, but mostly they're used to represent a point in 3D space or 2D space, right? So an X and Y coordinate is most of the time you could be seen as a vector. And in math, you'll see them with a letter with an arrow on top, and that is how they're represented. That is not entirely how we're going to be using them today. So this is a vector with 2 dimensions. Vectors have a certain dimensionality. This is a vector with 3 dimensions, and this is a vector with 8 dimensions. And they can have as many dimensions as you want. Well, I'll assume everybody here is some kind of developer. So if you see this, you're probably thinking, wait, this is an array of numbers. And that is actually exactly what vectors are. In our case, or how we can look at vectors. It's just an array of numbers, and the dimensionality is the length of the array, or the size of the array, or the count of the array. Well, it depends on what language you usually program in. So how do we use these vectors? Well, in 2013, our good friends at, well, Google, I see a Google Cloud shirt in the front, so, released the first model, embedding model that changed, that was able to change text into the vector representation of said text. So that is what such a vector representation looks like. And then after a couple of years, more and more things started to become vectorized or embedded. So images start to become embedded, and right now we can embed audio, video, 3D models. I think there is that's something that is heavily looked at right now. Point clouds, et cetera, et cetera. So we are like in a state of what can we embed, how can we embed as many things as possible. And that is done through the use of machine learning models. So these embedding models are machine-trained applications that are basically getting the input and giving you the vector output. So when you hear a bending model or embedding endpoint, that is exactly what it means. It's an endpoint where you can send your data and you'll get back a vectorization or a vector representation of said data. There are a lot of vectorization techniques out there. So some of them are, well, the first one was word2vec. A couple of released by Google. A couple of years later, Glove. And this had a really big problem. The problem they had, these embedding models, is they didn't understand context. So this, a word with different meanings in different contexts still had the same vector representation. And that made it really hard to, build application on top of it because you were never sure of the context. And then we had the transformer models being released in 2017, I just heard. And these models were very good at actually understanding context. So the same word in a different context would have a different vector representation. And that allowed us really to, build up those LLMs and all those applications that really allowed to do all cool things that you can see today. And right now we have, for example, the OpenAI clip, or Gemini, if you went to the Google talk a couple slots earlier, that are multimodal. So these models really can get different types of input, images, video, et cetera, and vectorize into the same vector space. All right, so that's what vectors are in short. So what are vector databases? Everybody knows what a database is, I'll assume. Check. So a vector database is a purpose-built database. It really has one purpose and one purpose only, and that is to store and index high-dimensional vectors. I tried to see, okay, can I use this as a time series, or can I use this as an event store, or something like that? Just don't. Just use it as a vector database, because they're really actually quite slow to put things in the database, and they're really quite fast to get things out of the database. So, so yeah. They index and retrieve using nearest neighbor search algorithms most of the time, not exclusively, but those are the most common algorithms. And of course, you can also store all kinds of metadata associated with your vectors, and then you can build your applications on top of that associated metadata. So somehow you can look at it as in the key to your object in the database is going to be the vector representation, and then everything you need is going to come with it. All right. What's kind of important, I guess, for people is, okay, let's say a tech illiterate project manager would come to you and was like, okay, I've been hearing about vector databases all year long. What are they? Do we need to use them? That is the answer I would give. That is a database that facilitates effortless and swift semantic search on your data. And of course, semantic being the keyword here, right? So if you just wanted fast search, you would just use Elastic or some proprietary application or solution. But if you really need semantic search in your data, then you can really start thinking about, okay, do I want to use a vector database here or not? What's kind of interesting to know is that while they are being exclusively used in AI applications right now, vector databases don't have to do anything with AI themselves, so there's no model embedded in the database or something. It's just a really sophisticated application that is very good at searching vectors and nothing else. So for example, you could, if you want to, you could put in your whole Minecraft world. Everybody knows what Minecraft is? Good. People with kids are like, yeah. So you can put the coordinate of every block in a vector database. As you move around, you can just keep retrieving all the blocks that are near your position. That's totally fine. It doesn't have to be a vector embedding as long as it's an array of numbers, right? That said, I tried, and it's a bit slow, so don't do that, but it works. If you want to be indexing in vector databases, there are a lot of algorithms. For example, linear search, very fun. As you can maybe imagine, it doesn't scale very well because every time you put in something in the database, it will check against every other object in the database where it's supposed to index it. But k-nearest neighbors is an algorithm that some of you might have heard about or not. Shout out to Spotify for approximate nearest neighbors. Oh yeah. Annoy and Voyager is the follow-up to that. And a personal favorite are hierarchical navigable small worlds. But yeah, I never really expected to have a favorite algorithm, but I guess here we are. And that happens with a so-called distance metric. So you can give up your distance metric for your database. Most of the time, they'll be using a Euclidean distance or similarity, and that is basically meters, centimeters, what you're used to. But it can be things like cosine distance, Hamming distance, dot product. It can be, well, you can even come up with your own distance metric, call it Alex distance, and hope it works. Do people know what the difference is between distance and similarity? No mathematicians, right? Yeah, okay. So it's a little bit confusing. If you're asking for the distance, you're asking how close are two objects from each other, and if you're asking for similarity, you're asking how far are two objects from each other. And I know some of you are looking at me like, you're saying exactly the same thing, but with different words. But basically, the distance, when two objects are close to each other, the distance is 0. And when two objects are close to each other, the distance is 1. The similarity is 1. Yeah, very confusing. But so it's between 1 and 0. So what's very important to know is distance calculation and indexing all happen within the so-called vector space. And you can define your vector space in different vector databases by multiple ways, so by schema or by table, by objects. Some do it automatically for you, some don't. But why they do this is to enforce you to always have the same dimensionality. So that you never check vector embedding with 512 dimensions against a vector embedding with 384 dimensions. Mathematically speaking, it's possible, but it will give you really janky results. So overall, they're like, okay, let's just not do that. Let's just for the same dimensionality within the same vector space. So yeah. But yeah, me being a gamer and hearing something called vector space, I figured, well, I can probably recreate that. So I tried to recreate exactly that, a vector space of my data sets that I'll be showing in a bit. So this is one data point in the database right now, and the planet associated with it. And as you fly around, you can see more database in my vector space. Now, I'll be the first person to say this might not be the most user-friendly way to explore your data, but it's the most fun way to explore your data. But what you really kind of want to see is, if you look around, these are all the data points, or the planets, and you see clusters being formed. And that is pretty much exactly what you want. So if we go here, you can see that everything close to this is semantically, so an axe and a whip, a little bit spoiler of what's to come, but semantically speaking, they are very close to each other. It's a weapon that you hold in your hand, short range, stuff like that. And this clustering is exactly what allows these vector databases to semantically search for whatever you need, because when you do a search and it's semantically close to a whip, it's going to end up, let's say, in this 3D space close to this point and return you the whip. All right. So if we look at the vector database ecosystem right now, after 1.5 years, 2 years, it has kind of solidified. I think these are the biggest one right now. But now also MongoDB and Neo4j, all the big database vendors also offer vector solutions. But I think these are the biggest ones. What is kind of interesting for you probably is everything to your right is open source, and everything to your left is closed source. I should move Elastic more to because I wasn't really sure what Elastic was, because they're being so secretive about their licensing right. But after talking to people from Elastic and kind of pushing through, it is closed source. Well, open, but not open source. Anyway, Red is exactly the same. But the rest, and for Postgres, you can download an add-on. It's called PG Vector. What's kind of interesting, some of these databases offer so-called built-in embeddings. So they'll spin up a Docker, most of the time it's a Docker image next to the database, which will automatically embed everything you put in, you try to put in a database. So that's kind of handy, because then you don't have to do calls to Vector, to OpenAI APIs, or to Hugging Face to get your embeddings and put them in the database. The database solves that problem for you automatically. So you just can say, okay, I want to put this in the database, and it will immediately vectorize it for you. Then, of course, some of them want to earn money. So they do that using managed services. For PG Vector, you can use Supabase, for example. You might have heard of it. It's like a Firebase equivalent. So yeah, all of them have managed services. It's quite expensive still, these managed services for vector databases, because there's kind of an AI gold rush going on, right? So I talk from experience. At least I found them expensive. What's also kind of interesting is how you query a database like this. Well, of course, Python is king in AI, ML, machine learning land. So all of them have Python clients, but some of them you can call through a REST API. Others you can call through a CLI or a JavaScript client. Some of them through SQL. And Vespa you can call using YQL, which stands for, I think, Yahoo querying language, which I've never heard about. So that was a first for me, which is quite interesting if you ask me. All right, so that's a little bit the ecosystem, how it looks like. So how would you go on implementing your own search directly in the vector database? So for our stack, I chose to use VV8 for persistence, a Spring Boot Kotlin backend application, because Kotlin is the best language on the EVM, changed my mind. And then for the front end, I'll be using Unity 3D. Anybody knows Unity? Yeah, okay, so Unity is a 3D game engine. It was in the news back in October, November for trying to enshittify their engine with all kinds of nice licensing costs. But yeah, so it's a game engine, and we'll be using that as our front end. So I chose VV8 because it's open source, so I can basically do whatever I want with it. So that was quite nice, and it's very modular. So I could really download images of different models and try and play with different models, see what the results were. The documentation is actually pretty decent, and the Java client is also pretty decent, which I really well enjoyed, to be honest. And it can run completely offline, which for me kind of remove some stress if I'm standing on stage giving a demo. So the architecture is actually also pretty simple for the demo. So we're going to have going to be talking to our Spring Boot application through REST. There we have the VV8 client library, which does calls to the Docker image through REST and GraphQL. Any architects sitting here? 1, 2, 3. So I had an architect some time ago that told me, okay, this can be simpler. Why don't you just immediately go from your Unity to your VV8 Docker instance? And to that, I have to say I'm a backend developer. Every day I work on backends. And if I see a chance to add an abstraction layer, I'm going to take it. Since abstraction layers are the best. All right. So for today, we'll be using cosine distance as our distance metrics, hierarchical navigable small worlds as our indexing algorithm, a BERT model for text vectorization, a RESTnet model for image vectorization, and a clip model for multimodal vectorization in the same space. So how would you calculate the cosine distance? Well, 1 minus the cosine similarity, makes sense. And the cosine similarity is something like this, math, math, math. But what's really kind of interesting, I think, for you is that if a vector comes back with a distance of 0.0, that means the two vectors are identical. And if it comes with a distance of 2.0, that means they're exactly opposite to each other. So for example, you get a Java class and a C# class, and you embed them, then the distance would be 2. Really? Doubt. But if you grab a JavaScript, script, and a Java class, then the distance would be closer to 2, probably. Unless you do some really funky things with your Java classes. But, All right, and then we have hierarchical navigable small worlds, which are a little bit trickier to explain. All right, so let's say these are all the data points we want to be putting in our database. What happens every time you inject something in the database or you try to put something in the database, it's going to do a proximity scan around the object that is entering the database. And then it will connect itself to an X number of nodes or other objects that are already in the database. In our case, that's 3. So every object that is entering the database will do a proximity scan for the 3 closest other objects in the database and connect itself to that. So it's building a so-called adjacency graph or a neighbor graph or a friendship graph. It has like a lot of names because in our industry we're really good at naming things. But yeah, so you're building a node graph basically with the X amount of closest neighbors. At some point, there is a random chance, I think this is 60%, that an object entering the database will be copied into a higher layer. And then it's going to do exactly the same thing in a higher layer. And then there's an even smaller chance, 30%, that it's going to happen again and it's going to be copied onto a higher layer. So you get this multi-tiered graph construction where the top graph is less dense than the bottom graph. And the bottom graph is actually the complete picture of all your data. Now what happens is if you do a search and the search ends here, and this is basically the object that you're searching for then, right? When it does a search, it's going to start from the same entry point all the way in the top graph and then find the closest node to where you are supposed to be. And then it's going to use that node as an entry point into the lower tiered graph to again go to the closest node and then use that again as an entry point in the lowest, most dense graph to find the closest node. So as you can see, we skipped a lot of checks and a lot of jumps by having this multi-tiered graph solution. Which to me is really nice and smart implementation to solving the problem of going through millions and millions of vectors real time and giving an answer back within milliseconds. So again, let's clean this up. We're searching for this object. Again, same entry point. We navigate to the closest node. Again, we fall down, navigate to the closest node. And then, again, we go all the way to the closest node. So, and you can also pass heuristics and all kinds of things on every node discovery. So a little bit like Dijkstra or A-star, sorry, where you can, influence how it searches for the closest node. So yeah, that's pretty cool if you ask me. Here, all right. Does anybody recognize this image? From what movie this is? It's from The Matrix, yeah. I was kind of surprised when people recognize it, just put two black. And we go, oh yeah, that's The Matrix. Anybody never seen The Matrix? Okay, good. So at least everybody knows what I'll be talking about. So there is a scene in The Matrix, right, where Neo is asking for a lot of guns, and then they give him a lot of guns. Super cool scene, but there is a very big plot hole in this scene. How is he ever going to find the guns he's searching for? So we're going to help Neo find the guns he's searching for. So we have a small CSV file with 3 properties, the name of the weapon, the type of the weapon, and the range of the weapon. So for example, Excalibur, and the type is sword and range is short. And then when this is vectorized, what happens is all these strings are concatenated to lowercase with a class name, which in this case is weapon. So then you get weapon, Excalibur, short, sword. If you want, you can even choose to vectorize the property name. So then you will get weapon, name, Excalibur, range, short, type, sword. So if you want to. In this case, we're not going to do that. And then through a BERT model, we're vectorizing this into 384 dimensions. All right. So yeah, I can imagine some of you are confused right now. Okay, this is just like the movie. I promise you, it is not the movie. So Trinity is like, are you sure you want to do this? I'm happy they did, because it gave us the elevator scene in The Matrix, which is just amazing. So now a little bit of a weird question. Does anybody have a favorite weapon? No? No? Sorry? A flamethrower, contrary. An RPG. I mean, RPGs send flames very in a compact form, I guess. But yeah, so if you look at the distance between the RPG and the flamethrower, it was at 0.68. So they're not necessarily very close to each other. But I put the max distance at 0.9, so it will return everything that is underneath a distance of 0.9, just to have results, right? So and if you look at the data set, it's actually very compact. Here we go. So it's just 50 weapons with just the name, the type, and the range. So very simple. But if we go, for example, a Japanese weapon, then you get an Odachi, which is actually a Japanese weapon. So it understands the context that an Odachi is a Japanese weapon, and semantically speaking, this is something probably you're searching for, and returns that. So it's pretty nice. Any Call of Duty players here? No one? Oh, one. That's why Activision was bought by Microsoft, I guess, huh? So an AK-47, right? Oh, an AK-47, very nicely in pink, which means it misses its texture. I should probably look at that. But again, so now we're searching for an AK-47. Here you can see the distance is much closer, so 0.19. So yeah, as you can see, you can really do some semantic searches on your even very compact data sets and try and find things you're searching for. Now, what is really interesting about vector databases, though, is given a certain input, You'll always get the same output, but you can never be sure what that output is going to be. To me, that is beautiful because I love gambling, but I can understand that some people are like, oh, this is not entirely what I'm searching for. So yeah, you never really know how an embedding model is going to vectorize your data. So it's really a little bit of trial and error. Okay, using this embedding model, do I get the results I expect when I search for this or when I search for this? All right. Let's go to a little bit more complicated data sets. Any Dungeons and Dragons players here? Oh, not any Harry Potter people that read Harry Potter? So instead of, when I say wizard, just think Dumbledore. And they're all pretty much close. All right, so a Dumbledore, or a wizard, is going to be strolling in the woods, and a thug is going to pop out of nowhere, and he's very forgetful. He has no idea which spells he knows and which spells he doesn't know. So we're going to help him by, querying for spells. So I put all the spells in the Dungeons and Dragons Player's Handbook. I put them in the vector database, and then we're going to query for that and see what we can find. And again, through a BERT model, hopefully we'll find something that can save him. All right. So. This is our wizard. The Dungeons and Dragons, do you have a favorite spell that you would like to see? Sorry? Speak to animals. Boring by speaking, I get it. Let's see what we get. So yeah, we get speak with animals, animal messenger, and animal friendship, which all three, are pretty similar to speak with animals. So for example, if we now do this, we cast a spell, and then we kill the thug. Yay. So now we're bringing back for Eternal Oblivion, really a Black Mirror episode where he dies every 5 seconds. So we can search for, sorry? A fireball. Firebolt or fireball? Hey. And again, here you see fireball, pyrotechnics, and firebolt. So it didn't even matter. You got them both. And then again, we can now a little bit more. So as you can see, it's the same animation, same particle, and everything. But we'll get to that. Spoiler alert. Yeah, if you look at the data set, though. Sorry. So this is how the data set looks like. So as you can see, it's a lot of text, it's a CSV, so it's machine readable, not necessarily supposed to be readable by a human. And I just put it, before putting it in the database, I had to do some processing. So that is also a really good thing to keep in mind, that there's a big chance, if your data was created in a way to be machine readable and not necessarily, readable by a human, you probably need to do some processing before putting in the vector database. So what I did here is I created a very semantic description of the spell and all the properties in the spell. So I said, okay, this is the name, the spell can be casted by these classes, this is the level, this is the magic school, it also has this material cost, etc., etc., etc. So I created a very semantic description of the spell using the properties of the spell to be able to make it easier for me to find what I'm searching for. And what I did here is when I created the schema for this object, I basically told VV8, I want you to vectorize the name property, I want you to vectorize the description property of this spell, so what I just created, and I want you to completely ignore all else. They're still stored in the database, so when you find an object or a spell, you can use all the properties to do whatever you want, but for the vectorization and the check on the vectors, it only uses the name and the description of the spell. So like that, you can try and help the embedding models to really create things, to really hit what you're searching for. An even better way to do this probably is to chunk the descriptions in a bit smaller chunks, and like that, see if you can find more easily what you're searching for. Because a lot of text will confuse the embedding model, right? So if you search with a lot of text, there's quite a big chance that you're going to hit something that you're not necessarily looking for. For example, if here I'll go, I would like to cast a spell, a spell that a wizard, that's what they're called, can cast and super cool and stuff. Then you can see that it gets a little bit confused and it hits a lot of things, especially because also the descriptions get quite lengthy. So here you would search for something that only a wizard can cast, and that is not necessarily what you got back. All right. So that is that. Now let's get on to images. Also pretty cool. Anybody ever played this game, Pokémon Snap? Or on the Switch. It also recently released on the Switch. It's such a weird concept to me. You are on rails, you just go in circles and you take pictures of Pokemon and you throw apples at them. And that's it. And it's hugely popular, it's insane. But of course we're gonna recreate it with a little bit of risk of Nintendo coming onto us with a lawsuit, but it's fine. So we have Ash Ketchum that really likes to flip his head, and then we're going to take a picture of a Pokemon, and through a ResNet 50 model, we'll try to find that Pokemon. So here I have a CSV with a lot of Pokemon, 721. I don't even know how many Pokemon there are right now. Any Pokemon experts here? So if I say, does anybody know which is Pokemon number 3? Anybody got an idea? And if I show the Pokemon? Almost. That's is it Venusaur? Yeah, I think so. This is Bulbasaur. Yeah. And number 6? Yeah, that's an easy one, right? How about number 25? Ah, everybody knows this one. But it's insane. I've had it that people went all the way to 200 and could name exactly which Pokemon it was. Like 240, and I don't know what the hell this is, but they knew. All right. So as you can see, the icons are not tagged, so there's no name of the Pokemon or whatever. It's just, this is the icon, and this is the number. And when we search for, we'll just get the data from the CSV based on the number of the Pokemon we hit. All right. So yeah, this is Ash, as you know him from the anime. We'll walk around. And this was Pikachu. Yeah, okay. No, let's see if the vector database agrees. Yes, so this is indeed Pikachu. So we take a screenshot of the frustum, of the camera frustum, or what the camera sees. We base64 it, send it to the database where all the icons are base64 stored there as well. And then we do does a similarity match and we find Pikachu. So yeah, that's pretty nice, right? So if we glide a little bit, apparently further, anybody knows which Pokemon this is? Beedrill, which makes sense, B. If we look from another angle, though, now it's Primplop. Oh, if we look from another angle, now it's Bisharp. So as you can see, it's a little bit confused sometimes. If I go, for example, over here somewhere, does anybody know this cute Pokemon? Mew, yeah, okay. Mew and Pikachu, everybody knows these. But I'm afraid it's Archen, whatever. So yeah, something weird is happening here, right? If you look at there on the bottom right, that is what the camera is seeing that sends the image to the vector database. So it doesn't see the whole world, it doesn't see the plants and everything, it just sees yellow plus the Pokemon. Anyone know what kind of yellow this is? It's Pikachu yellow. So yeah, the issue here is that the ResNet 50 model doesn't necessarily understand the context of Pokémon. It understands, and if it doesn't really understand the context in the image it's in, it's going to default to pixel colors and contours. And if it's going to default to contours, then we have a big problem here because all the images we use are the same. They are white background and very cartoony drawing, right? And the image we're taking is a 3D model that is moving. You have different perspectives and stuff like that. So matching onto contours is going to be really hard. So to solve this issue, you either need to train your model to, understand Pokémon, I guess. But training models is actually quite expensive. Or you need to train your model to, or you need to add more reference images. So what I could have done is take multiple perspective images of the 3D models I was searching for, put them in the database like that, and then it probably would have found exactly what I was searching for every time. But I found this a really kind of important thing to show you that you can't just put in your images or whatever you have in the vector database and assume it's going to work. You really have to kind of do some trial and error and things like that. We'll get to questions after the talk. Yeah? Oh. All right. So talking about images, we're back on to our Dumbledore again. But this time we're going to try to make it a little bit more interesting, a little bit more gamey, so to say. So we'll be walking around, and this time, once we find a spell, like we did before, we're going to grab the name of the spell and going to reference search it into an icon vector space to try and find an icon that matches the name of the spell. And that is done through a clip model that is a multimodal embedding model. All right. If you look at the icons, I don't have any CSV or anything. It's just the icons, just as they are, icon 1, 2, 3 to 200 something, 213. And this are basically what they look like. So there are 256 by 256, quite high res, nice icons. I bought this like 10 years ago from a Humble Bundle. I don't know if you know what a Humble Bundle is. You can just buy game assets very cheap. Back then, my mother was like, "You're wasting your money." Finally got to use them 10 years later. So yeah, as you can see, all these icons, they are not in any way labeled or whatever. They're just as they are. All right. So again, I have this personal mission to always show an explosion. So I was happy you said fireball. So I can start with a fireball. And as you can see, these are the icons that match the names of these spells. So a fireball, well, you could argue it's 3 fireballs. It's not 1 fireball on the icon, but it's still pretty close to it, I think. And then once we cast this, you can see. Thank you. So, and then we bring back for another round of suffering. Anybody that wants to see anything would be anyone that wants to try to break my demo, maybe? Ice Storm. See what we get. Storm of Vengeance, or Ice Storm, or Investiture of Ice. So then if we cast the Ice Storm, and as you could see, there was a different particle effect. So for me, what's really cool about this is with like minimal effort, I get an icon back out of like a huge icon database. And then I can just, in this case, what I do is I I calculate the average RGB color of the icon. And maybe very small here on the bottom, you can see that it's cyan. And that is one of the main colors, so they'll show a particle effect that is cyan or blue. And for example, if I do poison or I want to kill him with poison. A little bit more aggressive, you know? So then we're going to kill him by protecting him from poison. And then you can see it's a green. So yeah, so that is really cool. And you know, really with a really minimal setup, you can get there. Yeah. Do you had a? Sorry. Oh, it's okay. All right, I'll search for it's okay. Glibness, eye bite, or ceremony. So we do a ceremony, for example. Oh, it's again the fireball. Nice. So yeah, as you can see, yeah, it's pretty cool. So how about something like this one? I found really funny. I want to confuse them with JavaScript, and then you get back distort value. So I found that so funny. Coming from a type-safe environment, yeah, that is. So, or the big question mark in the middle, yeah. Spot on. All right, and then we break his legs again. All right. So yeah, as you can see, and if you look at the distances, oh, yeah, I should have not logged the whole base 64 image here, probably. Yeah, but here we are. So the distances are actually not necessarily, in this case, very close to each other. So it's 0.7, 0.75. So arguably speaking, they are pretty far from each other. All right. I'm also a huge metalhead. I don't know if there are other metalheads here. Any people that really hate metal music? Okay, good, because the next 2 minutes are going to be... so this is the band Deathclock. It's from the cartoon Metalocalypse, which is an amazing cartoon. And they have this jingle, the Duncan Hills coffee jingle, which to my opinion is the worldwide coffee anthem. So what we're going to do, we're going to try, is to create a Shazam-like application, but for metal lyrics. And as you know, metal, can get a bit heavy, a bit grunty, stuff like that. You have no idea what they're singing, etc., etc. So I have a data set or multiple data sets with songs from Beyonce, Billie Eilish, Lady Gaga, and I have 3 metal songs in there. One by Metallica, Enter Sandman. I assume some people know that one. Okay, I see some. Dragon Force, To the Fire and Flames, and Deathclock, the Duncan Hills coffee jingle, and that is the one that we'll be searching for. So how that is going to work is I have embedded in Unity, I have embedded OpenAI Whisper, which is an audio transcriber, so it listens to the audio and tries to transcribe the lyrics. On your left side, you'll see the lyrics that the model has transcribed, or so what it thinks it's hearing. On your right side, you'll see what the actual lyrics are that are being sung, and every half a second to 1 second, we'll be grabbing the last couple words in the lyrics, sending them over to the vector database, and trying to see if we can find the song that we're searching for that can match. So anybody that thinks, yeah, you're going to find it for sure. Anybody that is like, no way, you won't find it. Okay, so who is like, it depends? Oh, yeah. All right. So it's transcribing the song right now. It takes a little bit of time. And then let's see if we find what we are searching for. I did have sound, but I don't anymore. So let me quickly see. Yeah, these are the speakers. Any idea why I don't hear anything? Well, let's try again. Otherwise, I'll just remove it, and you'll have to listen through my beautiful laptop. Okay. I mean, I'm not muted or anything, right? Okay. And yes. Thank you. Ed Sheeran, Taylor Swift, yes. Billie Eilish, Ed Sheeran. Well, it's a metal song, not the one we're searching for. Billie Eilish, again. Selena Gomez, can be pretty metal, I guess. Post Malone. And what's really funny to me is, without fail, every single time, the guitar solo is Ed Sheeran. And I don't really know why. Maybe his voice is just very high-pitched, very sharp. So yeah, as you can see, we were not very successful in finding what we're searching for. So to that, I have to say, when AI eventually takes over and Skynet rises and they start dominating the world, if we just start to grunt to each other, they'll have no idea what we're communicating about, and it's an easy win. So yeah, thank you very much.